I think I don't need to introduce Professor Fu-Chun Zhang, but for those of young generation who may not be familiar with the name of Fu-Chun Zhang, let me give brief introduction of Professor Fu-Chun Zhang. I just studied his CV, so I didn't realize he graduated so ancient time. So he obtained his PhD in 1983 in Virginia Tech. Then he became the faculty members in University of Cincinnati from 1988 to 2006. Then he decided to move to Hong Kong, and he became a faculty members and also director of Center of Theoretical and Computational Physics in Hong Kong University from 2006 to 2014. Then he spent briefly 2 years in Zhejiang University. Then after that, since 2017, he moved to Beijing, and he became a faculty members of UCAS, and also few years ago, 2017, from then on to present time, he became the director of Kavli Institute for Theoretical Science. So this is only very, very brief history of his career. And he made many important contributions in strongly correlated electron physics and high TC superconductivity. And one of his most famous work is so-called the Zhang-Rice singlet. This concept, I think he published this paper very early in the day of high-TC cuprate, 1988 or something. And with this concept of Zhang-Rice singlet, it really paved the road for the study of strongly correlated electron system using TJ model and the one-band Hubbard model and so on. Since then, he published many papers in the area of high-TC cuprate and unconventional superconductivity. And more recently, although he's getting old, he become even more active working in topological material. So today and tomorrow, he will give us 2 lectures. Today about superconductivity. I think he is going to discuss about very recently discovered new superconductor, infinite layer nickelate, and its relationship to high-TC cuprate. And tomorrow he will give us seminar talk about Majorana fermion in topological material or topological superconductor. So with this, I will invite Professor Fu-Chun Zhang. And just before we begin, these 2 talks, today and tomorrow, is a lecture series. So time constraint is rather flexible. Basically, he can have 1.5 hours, between 1 hour and 1.5 hours. So among the audience, if you have any question, I think you can, in the middle of talk, at any time you can ask question using audio or using chatting window. With this, let's welcome Professor Fu-Chun Zhang. Okay, with the big upload.
Okay, well, thank you very much, Professor Bang. It's my pleasure to give the two Zoom seminar. So let me just share. I'll share the screen first. Okay. Let's see. Okay. Can you see me? Okay. So I first I like to in today's seminar I'd like to talk about our recent work on the theory for superconductivity in infinity layer nickelate. And I will emphasizing similarity with and the difference from the high TC cuprate. So let me make sure the voice, the sound is fine. Hello?
Yes.
Can you hear me?
Yes, yes. Sound is
Yes.
fine.
How about the screen?
Screen is also fine.
Okay, yeah. I'm a Fu-Chun Zhang, as Professor Bang introduced. I'm now the director of Cavalry Institute for Theoretical Sciences at the University of Chinese Academy of Sciences, which is located in Beijing. Let me say a few words about my institute. This is one of 19 Cavalry Institutes worldwide. Our mission is to conduct first-class research in theoretical sciences, which mainly will cover physics, but also may touch biology and mathematics. And the other mission is to organize international and domestic workshops, summer schools. We have a lot of visiting programs, so welcome you to visit us after this pandemic. Currently, we have 10 faculty members in our institute, including several in condensed matter theory and a few in particle physics. And our target is to have 30 faculty members. And we also like to have the institute to be very international. And we are collaborating with many other institutes, including APCTP. So you are welcome to visit us, okay, in future. So let me just start with the recent discovery of superconductivity in an infinity layer nickelate. So this is reported about a year ago by Howard Huang, professor in Stanford. So first you may ask why this is interesting, because the TC was observed only about 14 Kelvin. Okay. So the reason is nickel is just next to copper in the transition metal in periodic table, and nickelate superconductivity, if discovered, will be a confirmation to some extent to the model for high TC cuprate. And despite 30 years effort, nickelate superconductivity was not found until last year. So that's the reason people are interested in, I myself get interested in. So let me just tell you what I will talk about, okay. And because the discovery in experiment on the infinity layer nickelate actually to some extent confirmed that the 2D Hubbard model or its strong coupling limit of TJ model may be superconducting. And that was the first proposed by late Phil Anderson for the high TC cuprate. I will discuss the similarity difference between nickelate and high TC cuprate and present our recent theory for the low energy physics and the superconductivity in the nickelate. And these are my collaborators. We have two papers, one published with Guangming Zhang from Tsinghua University and Yifeng Yang at IOP. The more recent work on the superconductivity is collaborated with my student, Zhang Wang in KRTS. Okay. So here's my outline. I will give a brief introduction and give a brief review of so-called plain vanilla RVD, resonant valence bond for high TC cuprate. The emphasis will be on the TJ model and projected superconducting state. And then I will talk about our model for parent compound of nickelate superconductor, which is the TJ Kondo model, we call it. Then we study the superconductivity within the model and make a prediction about the parent symmetry for the nickelate superconductivity. Here it's just, we predict the D plus I S wave pairing at light doping and the D wave at heavy doping. Okay. So let me briefly review the superconductivity prior to high TC. The superconductivity was discovered in 1911 by Arnold. And Meissner effect, which screens the magnetic field, was discussed in 1930s by Meissner. And then, of course, we have London theory, phenomenological theory for superconductivity. Ginzburg-Landau theory was developed earlier for 1950s. A successful microscopic theory, Martin-Cooper-Schrieffer theory, was made in 1956. Okay. And that BCS theory is based on two things. One is starting from a Fermi liquid. The second is they have attractive interaction. Okay. The electron-electron interaction is due to electron-phonon interaction to get attractive. And they show that infinitesimal pairing will lead to instability of Fermi liquid towards the superconductor. So BCS, as we all agree, it's one of the most celebrated theories and confirmed by many experiments, such as Cooper pair 2E and the Josephson tunneling and the change of the phonon spectrum near TC. So this is just a slide for the BCS theory for conventional superconductor. So what you can see is the electron here with a two negative charge. One electron interact with the lattice. Okay, the second electron gets in, will get energy. So that's the basic the picture for the electron-electron interaction via electron-phonon coupling. In the theory, the angular momentum is equal to 0. It's a spin, it's a singlet. However, the high TC superconducting cuprate is very different. That was discovered in 1987. It's a strongly correlated system. And the normal state is not a Fermi liquid. And the superconductivity not from electron-phonon coupling. And the basic yes. Any question? Oh, short. Okay. And the basic physics is on copper O2 plane. The parent compound, that means such as lanthanum 2 strontium 04, it's an antiferromagnet, not insulate, well described by spin 1/2 Heisenberg model of star lattice with the coupling J about 0.1 eV. And the whole doping induces superconductivity, which is quite well described by the T prime J model. And for high TC, it's not S wave, but it's a D wave pairing, evidenced by a number of experiments. And there are many other instabilities, such as stripe, density wave, charge density wave, pneumatics, which are still under active investigation. So those more complicated phenomena, stripe, all this, I will not touch in today's seminar because they are very interesting, but they are currently still in the investigation and not so probably relevant to the nickelate I want to discuss. So that it's the phase diagram, the ITC cuprate, and this is the temperature, okay. And this horizontal is the whole doping. We can see that in the undoped case, it's antiferromagnet, not insulate. And the doping drives to superconductivity. Yes, I hear some comment or some questions.
It's
so,
yes. We are sorry. Somebody might turn on their audio. Please turn off all your audio. Thank you. Fu-Chun, you can continue.
Okay, I continue. Okay, yeah. So this phase diagram I copied from about paper by Keimer et al. 5 years ago. Okay, and so basically what I will emphasize is just two phases today. I think more prominent is antiferromagnetic and superconductivity. Okay, it's here for cuprate, it's a D wave. Okay. For nickelate, as you will see, there's no antiferromagnetic. So we'll explain why. And for nickelate, the pairing superconductivity, whether it's S-D wave or more complex, and it's not clear in experiment, but we made some theoretical analysis and predictions. Okay. So this is a crystal structure of high TC. It's a layered copper O2 plane. And there are many elements. Okay, for instance, I consider this, but I want to focus on this copper O2 plane. This is a copper O2 plane, okay. And that's the chain in the YBCO. And all these high tissue cuprate have a common element, this copper O2 plane. Yeah. And you may ask whether others are relevant. Okay, in the very beginning, people made an argument that this copper O2 plane is most relevant, or others just building blocks to make the system stable. And actually, recent paper by Yunkyu Zhang in Fu-Chun University, published last year, has confirmed that two-dimensionality is important. Only that one layer, actually in that compound, they have two layers, okay? And the physics, the properties like TC and this STM measurement, essentially the same as the bulk. So that means the third dimensionality really plays not much role. Okay, so we can focus on 2D systems. So that makes life much simpler. We have such a copper, this, okay, and oxygen, the plane, we can temporarily ignore all other element, okay. And this is a picture for parent compound, like a lanthanum 2 copper O4. And so at each site, we have just this is a copper 3D x squared minus y squared orbital, which is partly, it's singly occupied, or other orbital on the D are completely occupied. So I use a hole notation. So just one D hole at every site. The reason the system does not like two holes on the same side because of Coulomb interaction. The Coulomb interaction here repel each other, which forbid double occupancy of the two holes. And then the super exchange between the two neighboring holes will give us this J. It's antiferromagnetic, which is order of 0.1 eV. And so the model for the parent compound is well described by the Heisman model in a square lattice. Okay, and the neutron experiment actually strongly confirm this. The system is antiferromagnetic. Okay, and the excitation spectrum is very much consistent with the Heisman model's result. So this is a spin 1/2 2D Heisman model. So what the most important advance in that direction was made by Van Anderson, who proposed a TJ model for the system. And so he made that conjunction theory in 1987, just a few months after the discovery of high TC. And we wrote a review type of article we call the plain vanilla RBB theory for high TC. Okay, so that contains a few important things. The first thing is the model. We call it TJ model in 2D square lattice. That's because you dope lanthanum by strontium or casing. You introduce additional hole. That hole will be on the copper O2 plane. Okay, so that gives you this Hamiltonian. It's allow the hole to hop. It's described by T, and the neighboring spins intact described by Heisman model. The important thing about this model is a constraint. So every site, I allow only either one electron or no electron. You do not allow these two electrons get together. Okay. So, and it's a close relevance. I think that's what Professor Bang nicely introduced. I made with Professor T.M. Rice in Zurich soon after the Anderson proposal to make Van Anderson's proposal more examine the proposal and more mathematically tractable. So the other important point in this plain vanilla RBB theory is we use a variation of project BCS state. And that also was made by Van Anderson and other people, including like Kautlia, and myself, just carry out this calculation, I think, more carefully to examine the system and predict the D wave. So what this so-called projected BCS is like this, because every site we do not allow two electrons. Okay, so it's that constraint make quantum mechanics much more complicated. We call the projection. And how do you write the wave function with the projection? And Van Anderson proposed a BCS because we study superconductivity. So we use a BCS wave function, but just add a projection P here. Okay, this P is a product of 1 minus n spin up and spin down. It's just a projected W occupied state. Okay, so the calculation, exact calculation is the variation of Monte Carlo, but analytically we can do some approximation. Okay, and those detailed study of tri-wave function leads to a D-wave symmetry of the pairing, which was confirmed in 1994 by crystal experiment, and also consistent with RPES and many other bulk measurements. So with that, I like to go to this discussion of the nickelate. Maybe I just stop quickly, see any questions. Okay, if no question, you can ask later. Now I just come to nickelate. Okay, and that was discovered last year. So first I will just introduce phenomenology for nickelate. Okay, some major experimental result. So one is what you see here in the left, upper left figure. Okay, and this is the parent compound, neodymium nickel O2, and that you can see it's an insulate. Okay, and resistivity, just as function of temperature, reduce, then turn up. Okay, and now we compound. This is a very important point. And the doping with strontium, which you replace like 20% of neodymium, make the system to be superconductor. As you can see, this transition is about 14, around 14 or 16 Kelvin. Okay, and this upturn, we will argue, actually it's consistent with the Kondo physics, because what the Kondo proposed is due to the magnetic impurity scattering that will turn out. Okay, and the system here is not antiferromagnetic. It even lowers the temperature you can reach. So this is different from cuprate. However, doping makes a superconductor. This is similar to cuprate. The lower left panel is the Hall coefficient. Okay, and again, this red one is the parent compound, neodymium nickel O2, and the doped one, the superconducting, is like this. What you can see is for the parent compound, the charge here is one type. This is negative. However, when you dope it, you have two charges. Okay, they're turning around. Two type of charge, electron and holes. Okay, so resistivity, as you can see, it's a paramagnetic metal at high TC. Okay, and these two types of charge carriers. So the question is why the resistivity has an upturn below like this 50 or 60 Kelvin, and the Hall coefficient has a negative increase. Okay, at the upper right panel, it shows the resistivity as a function of temperature for a various magnetic field. Okay, so this is zero field, so the resistivity, actually the superconductivity, is reduced, suppressed, or destroyed by magnetic field. Okay, so this is the phase diagram, superconductivity and normal state. So the other experiment is the lattice constant along z direction is changed after doping. Okay, and they plot superconductivity as a function of this strontium doping. Okay, so this is like M shaped. Okay, it's up and down and up like this. Okay, so these are some phenomenology. So the same group, Daifeng Li and Harold Huang, has made this picture to show two types of carriers. Okay, and this is again the left, upper left panel is a Hall effect measurement, and they plot Hall effect as a function of doping, strontium doping X. Okay, so you can see this is some kind of the electron. This is some kind of hole picture. So data can be measured from the Hall experiment. So that means dominant charge carriers change from electron to hole. Okay, when you increase the doping like X. And actually the structure Fermi surface is also changed as the strontium doping increases accordingly. And there's independent experiment by Zhang et al. I think that's the Haihu Wen's group in Nanjing University. Basically get the same picture as what Harold Huang's group on the two type of charge carriers. Okay, that means at the low doping, it's the dominant charge carrier is electron, and this is dominant charge carrier becomes a hole when you increase doping. So now I will describe the theory for parent compound of nickelate superconductors. Okay, so that it's a paper showed I think several months ago with Guangming Zhang and Yifeng Yang. Okay, so actually initially you would expect this nickel oxide, neodymium nickel oxide, is very similar to the cuprated parent compound. Okay, for instance, this is a picture. Okay, and that's the nickel, red one is oxygen. This is neodymium. Okay, so you have 4 oxygen around each nickel and 2 nickel neighboring with 1 oxygen. Okay. And the simple electronic structure tells us that, and this nickel here is 1 plus. Okay, so the x squared minus y squared orbital of the nickel 3D will be left. So this is more, I think, the most relevant part. Okay, if so, then we will have a Heisenberg model very similar to the cuprate. Okay, and in passing, I will show that I will just inform you that the J here is much smaller than in the cuprate, because that energy atomic level between D and 2p on the oxygen is much larger in nickelate. Okay. So the question qualitatively, why we do not get this Heisenberg model simply for nickelate. Instead, they found not antiferromagnetic. Okay, and that is related to, I think, the question about why the charge carriers come from. Okay, and how the antiferromagnetic non-range order is suppressed, and what is the nature of the normal state metal, and what is the effective model Hamiltonian for nickelate superconductor. Okay, and quite 16 years ago, actually, there was a paper, first principle calculation by Warren Pickett. Actually, at the time, they calculate this electronic structure for lanthanum nickel O2, which is believed to be similar with neodymium nickel O2. Okay. They found that there are 2 things. One is reduced nickel 3D oxygen 2p mixing, okay, due to the increased separation of the site energies, ED minus EP. That makes this Heisenberg exchange coupling J much smaller. The second, probably more important, is mixing of nickel 3d square and lanthanum 5d orbital, which will lead to a Fermi surface pocket. So that means here the lanthanum 5d electron comes out. Okay, if I use neodymium, it's the same. You have a 5d electron will come out. So things are more complicated than cuprate. Okay. And this X-ray inelastic, resonant inelastic X-ray experiment actually indeed found a small Fermi pocket in this. Okay. That was also carried out by Harald Huang's group in Stanford. So that explains there's a difference between, in particular, between the parent compound of nickelate superconductor and the cuprate. Okay. Now I like to emphasize the resistivity at a lower temperature. Okay. So what I like you to see is this is red one is resistivity versus temperature. Okay. And the dashed line here is a log T. So at the low temperature, like from 50 Kelvin, around that, okay, actually you can see the experimental data can be fit very well by log T behavior. And that is a strong indication for the quantum physics that tells us that, suggests us that this resistivity upturn is due to the Kondo effect, because in the Kondo effect, the conducting electron will be scattered by magnetic impurity, which causes additional resistivity. Okay, and that it's also negative Hall coefficient. It's similar. Okay, and the lanthanum nickel O2 actually show the similar transport properties in the resistivity, and also fit quite well in this temperature regime. Okay, by the log T, and at a much lower energy, there's something deviation from the log T behavior, which we do not understand completely for this. So that Kondo effect actually has been a very tremendous phenomenon. Okay, first observed in 1930 and was explained by Kondo in 1960s. Okay, so what you can see is usually you would expect that kind of the blue ones, Nobel metal, and okay, and this is probably the green ones. Okay, you have metal become superconductor, but the alloys with the magnetic impurity show upturn here. This is log T behavior. Okay. And we can fit that parameter like the Kondo coupling J or Kondo coupling K quite well with the Kondo temperature. So you may ask the question, where are the magnetic impurity come from for this compound? Okay. One possibility is a neodymium 4F electron, which has a magnetic moment 3/2, and nickel moment is a spin 1/2. Okay. However, if I consider lanthanum nickel O2 has a similar behavior, then lanthanum has no 4F electron. Okay, so the conclusion is the conjecture is must be from nickel spin 1/2. Okay, so we now propose this a picture for the parent compound of nickelate superconductor. Okay, so let me focus on the right panel figures. Okay, so this is the picture, and we have this green is a nickel 3D band, and there's a rare earth like neodymium or lanthanum 5D. Okay, and there's overlap between this 5D, lanthanum 5D or neodymium 5D electron with the nickel. Okay, So the Fermi surface mainly will be the nickel 3D electron, but with some of the lanthanum or neodymium 5D. So if I draw this lattice, then what we have is like this. I have for every nickel site, I have either spin up or spin down. The reason is they don't like to have 2 electrons or no electron because of Coulomb repulsive interaction. Okay, and I have this. However, I have this conducting electron coming from rare earths. Okay, and they interact with the nickel local spin to form a condo singlet. So like this one, it's a condo singlet. Okay, the red ones are lanthanum or neodymium electrons. So they will be captured by local moment. And because the total number of electrons is 1 average per site, so if I have 2 here, 2 electrons, so I must leave some holes here. So this picture is in average 1 electron per site, okay? But in addition to the spin up or down, I have represented by blue arrows, okay? I have holons, which carries no charge. I have doublons. The doublons here, just the condo singlet. I have 2 electrons, okay? So that maintains average electron 1 per site. In mathematics, I have number of holes here, okay, equal number of conducting electrons. The only issue is the conducting electrons is captured by local moment to form a condo singlet. So this is our cartoon picture for the model. We call the self-doped Mott insulate.
Okay. Can I ask something?
Yes, please.
Yeah, so here, this situation is for the undoped system, right?
Yes.
So and once you doped, can you comment what would happen?
Yes, I can briefly say a few words about that. When you dope, okay, that means you introduce holes here because you use strontium to repress neodymium. Then the simplest way is to add more holons here.
Mm-hmm.
And at the same time, because of a change of the chemical potential, the number of doublons may be also reduced.
Mm.
So the undoped system, I have, we call a self-doped Mott insulator. And that means the number of holons equal to number of itinerant electrons. Okay, and these itinerant electrons are formed condo singlet with these nickel spins. So I can call the doublons. Actually, it's not as localized as I draw, but this is a cartoon picture. Okay.
But in this case, holon is delocalized, I guess. No?
Yes, they are initially they are delocalized conduction electrons.
Mm.
But when you lower temperature,
Mm-hmm.
they are screened by the magnetic impurity.
Mm. I see.
So similar to the condo lattice, but not all the nickel spins are screened.
Mm.
So it's between condo impurity and the condo lattice. Some of the nickel spins are screened.
Mm-hmm. So then it's probably conducting, strictly speaking, no?
Yes, at a high temperature they are conducting. Actually.
Okay, I see.
But at a lower temperature, as we say, it's at a certain temperature, we call the T naught, and they are basically will be localized.
Mm. Okay, thank you.
Yeah. So this is, I think the picture is between condo lattice and the condo impurity. It's okay.
I have question.
Yes.
So at the beginning you said the localized nickel spin is screened by lanthanum or neodymium 5D electrons. So in this picture, this 5D electron themselves already form Fermi surface or not?
Say again.
So
I understand your question about we have localized nickel spin. We
right.
have delocalized or itinerant, let's say, lanthanum conduction electron.
Right. So that's my question. So in this cartoon picture, you assume nickel site is without doping. Nickel site is all localized with one electron per site or one
Yes.
hole per site. Okay.
It's less than one site, one electron per site. I have holons. What I want is the total number of electrons. It's one per site. When I say total number of electrons, I mean include both nickel electron and lanthanum electron.
So my question is, when you say this Kondo screening, this conduction electron comes from lanthanum 5D electron, or it comes from nickel self-doped electron?
Oh, that's coming from, yeah, good question. That's coming from lanthanum conduction electron.
Right. If I understood it that way, you don't have self-doping. Why did you say self-doping? Nickel site is all one hole per site.
Yes, that's the name. I think okay, that's the terminology. What I consider self-doping is I assume if all these they do not move. Okay, that we call it condo singlet is double because the double electron here.
I see.
And I have holes here,
Mm-hmm.
right? So in principle, this parallel compound. Actually, you have holons, you have doublons. They can move around.
Right.
Yeah. Experimentally, we do not see that superconductivity. That's I think the reason is because it's very dilute.
I see. Anyway, the main point I want to make sure is that in your model, without doping, the system already has a Fermi surface which comes from lanthanum or neodymium 5D electron.
Yes.
Yeah. Okay.
Yeah. That's. I think this is probably widely accepted.
I see.
And they are because the experiment fact is this is not antiferromagnetic.
Okay.
In the parent compound.
Okay.
That's the one thing. The second is because the first principal calculation, they see some kind of, two type of electrons at the Fermi surface, like by Warren Pickett, and more recently by anyone, It's so this is, I think it's all pretty much universal. Whether the question, whether this conduction electron will screen, okay, the nickel, that is not everybody agree. Okay. So we are the I think the first to make the proposal that conduction electron will screen the nickel electron. The reason is I think the controversial or the issue is a little bit settled because as I said, it's very natural to have this conduction electron to screen that. However, if you do band calculation, there's a coupling between them. How big is the coupling? So that is an issue. I think a different first principle calculation give you different the kind of coupling. Okay, but in our model, we consider the coupling is large, and they do screen the local.
Okay.
Okay. Okay, so shall I, because this is important the point, it's a simple, but it's a no, it's a phenomenologically, I think it's important. Okay, thank you for your question. So that's the picture. Then mathematically, how do we consider? So we consider model Hamiltonia, including two parts. One is the TJ model, the HTJ, the other is the HK condo part. Okay. The TJ model actually looks identical to the TJ model in cuprate. Okay. And of course, hopping integrals, J's can be different. Okay. And the condo part, here I include the condo, the TC. It's the C, it's the conduction electron from the 5D lantern. Okay, can hop. And then there's a condo coupling. That S means the local spin of nickel, and the C's are the 5D orbital. Okay, so this is the condo part, and this is the conduction part. So that's our proposed Hamiltonian. Okay, and we consider the lower carrier density limit. This is much more smaller than 1, maybe 5% or 10%, or the kind of small number. Okay. And it's interesting to note there's a paper 20 years ago by Anthony George and his collaborators. What they found in their calculation, okay, they found the low energy regime condo lattice model actually displays the incoherent condo scattering. Okay, so because we are considering many impurity, okay, but it's not a simple impurity. So what they found is the condo lattice is also show this incoherent condo scattering, which we needed to explain the experiment finding. The upturn resistivity turn as a function of temperature below T, like 50, 60 Kelvin. Okay. And so the model we have include, I think, the condo physics and multiphysics are combined. So probably it's an interesting, okay, model to study correlated systems with unconventional superconductivity. Okay, so of course we did some calculation, some select boson calculation to show, you know, that the condo effect, even we have like a small doping. Okay, but I like to go back, go on to study the parent symmetry of nickelate superconductivity with that model. So that we have a preprint a few months ago posted, okay, calling parent symmetry of superconductivity in infinity layer nickelate. Okay, so we have this model. Let me just go back to, okay. So this is our model Hamiltonia. It's we call the TJ condo model. Okay, so how to study the superconductivity? It's a lower temperature, because there's a constraint on the nickel side. Okay, you allow 1 electron or 0 electron, but no two electron. Okay, the case. So we adopt a technique we developed many years ago, actually at the time with Maurice Rice and Gross and Shiba. Okay, we call that renormalized mean field theory. Okay, to study the superconductivity of the model. So that theory is basically to replace the constraint by a number of several just renormalize the constant like GT and GJ and GK, those, okay. So this is related to the Kurzweiler renormalization fact. So now we have effective Hamiltonian, which we're acting on not projected helped space. I release the projection on, okay. But I have this renormalized parameter. Important to see is this renormalization factor here is proportional to the whole density. If NH equals 0, then of course you cannot hop, okay. And the renormalization of the spin-spin interaction is enhanced, okay. And I have also renormalized the condo effect. This essentially is enhanced by factor 2, okay. Then we do this mean field theory, okay. You have J term. J term is given by here. You have the parent term. I introduce this particle whole, okay, and a particle. That's the pairing, okay. And here we assume it's even pairing, okay. For the condo part, this K part, we have introduced also two parts, okay. One is this D diagram C, okay, C diagram, this is the particle, this is, okay, again, it's a pairing part. And it's important to note before we do calculation that the J term from the spin-spin coupling in favor of a D wave, okay. That's we learned from cuprate, because you want the chi to be like a isotropic along X and Y. So this pairing should be, right? Yeah, pairing should be just a different sign along X and Y, okay. On the other hand, the condo part actually in favor of S wave because it's on-site, okay. It's between the nickel electron and the conducting electron of 5D. So these two, actually, it's interesting to know that they're competing each other. And then with this mean field, we can solve these Bogoliubov equations, okay. And this is the main result I show you, okay. So for certain parameters like TC, it's the hopping integral of the conducting electron versus the K, or condo coupling, okay. For this equal to a quarter. What I want to emphasize is this is a pairing multiplied by this GT, okay, the renormalized factor, such that at no doping, there's no pairing, okay. So it's different from the mean field pairing, just multiplied by additional renormalized factor. And I have decomposed the pairing in terms of the S wave part, the blue ones, and the dashed ones, it's D wave, like this, okay. So there's actually you can two regimes. In the lower doping regime, I have both component of the D and S, okay. The lowest energy state actually is given by D plus IS, because that make the gap larger, okay, to gain more energy. However, as you increase doping, actually the 0.1514, okay, so the S wave pairing disappears, okay, and the D wave pairing enhanced like this, okay. So that means in this regime, actually I have D plus IS, and in this regime, I have only D wave part. Okay. In the calculation, we make a simple assumption that we fix the number of conducting electrons, like 5%. Okay, so we do not change. Actually, realistically, probably this number will be also reduced. Okay, And these are just the Fermi surface, okay, with doping like 0.05, doping 0.2, okay, the Fermi surface change. I have 2 Fermi surface. So in the parameter, we use in this nearest neighbor, t equal to 0.1, and next nearest neighbor hopping t prime equal to minus sign 0.05. Okay. At the right side panel, what I show you here is actually, this is the condo totally dominate. Okay, so it means a small bandwidth of the conduction electron. Actually, in the competition here is S wave wins the large doping. Okay. I think experimentally probably more relevant to this regime. Okay, so the main point of this TJ condo model is that the parent symmetry, there's a change when you dope, okay, from like a D plus IS to a D wave pairing. When I say D wave pairing, I mean that probably is similar to cuprate, okay, but at the light doping situation can be quite different. So that is the phase diagram from the TJ condo model, okay, and I have this parameter for the conduction electron hopping versus the K, and this is a doping ratio, okay, and the important thing is this light doping is D plus IS, okay, but here it's the D wave, okay. And it's interesting to note that there's a recent experiment. They did for these materials, neodymium 1 minus X, strontium X, nickel O2 film. Okay, and the sample, of course, as you know, when you do STM, there's inhomogeneity of the sample. Okay, and they found 2 different places. One is like this. Okay, this is the 4 superconducting gap, and this is like a nodal superconducting gap. Okay, and we may interpolate this is consistent with the D wave because there's nodal, and this is consistent with the D plus IS because D plus IS is nodaless, it's 4 gap. Okay, and this is in the same sample in different location, which may represent different doping in this sample, okay, which is quite common in strongly correlated systems because of due to the inhomogeneity. Okay. So at least why we'd be cautious, say that the experiment confirms our theory, but we can say that the theory is consistent with the experiment because of the 2 type of gaps. Okay. I think it's running for 1 hour. I'd like to just give a summary. Okay. So in this talk, I briefly reviewed the cuprate superconductivity. In comparison with the cuprate, the nickelate superconductivity, it's similar, but it's slightly different because of the self-doped multi-insulate. Okay, because of the neodymium 5D or lanthanum 5D conduction electron. Okay, where they couple to localize the nickel spin to form condo singlet at a lower temperature. So that's our picture. Okay, that's the parent compound. When you dope, you just introduce more holons here. Okay. With the strong doping, we found multiple superconducting phases with an induced transition accompanied with the Fermi surface reconstruction. Okay. I think thank you very much for your attention, and be happy to answer questions. Thank you very much.
Okay, thank you very much for very nice and interesting talk about newly discovered nickelate superconductor. So session is open for the question. Please ask question. Okay, while we are waiting from audience.
May I ask a question about the doping?
Yes.
So you have shown us in the last slide a phase diagram with doping and doping ratio, but I mean, the kind of mechanism you're describing, it's making us, I guess we can wonder about, you know, whether all doping mechanism would give us the exactly same phase diagram. For instance, if instead of doing niobium substitution, we're actually reducing oxygens, would you predict same phase diagram, or would you predict different phase diagram?
Yes. You mean this phase diagram?
Yes.
Yeah. Yeah.
So this is.
You see, this is of course simplified. When we do calculation, we fix the NC, the conduction electron, NC as 10%. Okay, that means I fix this, but I change. I have more. When you dope, you have more holes. So this is the calculation. If I allow this NC, when you dope, this NC also reduce. Okay, and I would expect probably change more rapidly. That's my prediction. Just the effectively doping ratio P here can be rescaled, similar like that qualitative.
I see. So here you didn't specify any doping mechanism, but actually, depending on doping mechanism, NC may be fixed or it may change.
Yes, I think that's qualitatively, I would argue when you dope, NC also will be reduced. But how it reduces, it's more complicated. I think I need some input from the first principle calculations. We can do that. Yeah.
Okay, thank you very much.
Yeah.
Okay, I have a question. So in your model, you always assume two different forms of peace. Am I right, first of all?
Yes.
So then first question is, for example, when you find the gap solution D plus IS, how can I visualize this gap function D plus IS on each Fermi surface? Because when you show this decomposition of S-wave part, that's
Yes.
a combination of C electron and D electron. So in the Fermi surface picture, how can I visualize this S component?
Well, that's this is interesting and important question. The conducting electron and the nickel electron actually hybridized. That it's so this is I think it's the Kondo picture. So they coupled together. So so Kondo picture involved two different type of electrons. The nickel or lanthanum. Okay, and the D part only I think are most relevant to the nickel electrons. So I think then mixing, because the S-wave part actually is the coupling between nickel's electron and the lanthanum electron. I think that's you can, if you consider, so that means you starting from the non-interacting Fermi surface may not be the good starting point, because we have here you have counter coupling. You know your electronic structure is completely reconstructed.
Yeah, fine. But you solved your model in any
Yes.
case by mean field decoupling. Can you show us the one of your slide? Yeah, this one.
Yeah.
So you draw some form piece.
Not well. This is the lower doping that I have with D plus IS. Okay. This is large doping. Large doping I have only D wave here.
Or you have only D wave.
Yeah, large doping I have either D wave or as in this case I have only D wave.
So then, for example, in this second case, large doping, the formulology, you have two Fermi surfaces, then your solution said both two Fermi surfaces has D wave pairing symmetry.
Yes, I think the second one is this D wave is dominantly by these nickel electrons. Okay, and that one you may consider is due to the proximity effect.
I see. Yeah. Then when I look at the left-hand side, smaller doping, there you have only one Fermi surface, or?
Yes. And I have only one Fermi surface finally within the mean field solution. It's not the original electronic calculation by Warren Pickett and his collaborators.
Yeah. Then in this one Fermi surface has D plus IS gap symmetry. That's the solution.
Yes.
I see. Okay, then one last question is, according to the tunneling experiment by Hao Hui Wen, he shows both S wave-like and D wave-like tunneling data. Then you said this is consistent with your scenario, but for example, left-hand side, suppose you have really D plus IS pairing gap. You do not expect this kind of very U-shaped full gap S-wave feature. If you have D plus IS.
Yes, I think, I think we plot more precisely what the shape is, okay. But qualitatively, I think D plus IS, there's no nodal. So you would see it's flat. Okay.
Of course, you should have full gap, but
whether any features away from that, it's more complicated.
All right. All right.
You're right. Yes.
That's fair enough. Okay. Thank you. Any other question from audience?
So is there time? So time reversibility breaking is confirmed?
Yes. Yes. It's D plus IS break time reversal symmetry pair. But experimentally, probably it's so far nobody has done any curve effect or nuance spin rotation experiment. Has not been that level. RPS is more difficult. I think Huang's group they probably can difficult to do the STM. So the sample is still they improve. They are improving the sample quality such that more experiments can be carried out.
I see.
Good. Any other question?
Can I ask one question? So in your calculation, you mentioned that the number of conduction electrons is expected to be constant. So it means that upon hole doping, the dope hole goes to the nickel x square minus y square orbital, not the rare earth 5D metallic band?
Yes.
Thank you.
Yes, can you, what's your question? May I?
So in the PAMI surface, the one is the nickel X minus Y scale, and the other is the rare earth 5D band. So I think that upon Hall doping, Hall also goes to the rare earth 5D band. So it means that the assumption of the number of the conduction electron constant is not correct, I think.
Yes, you are right. Yes, you are absolutely right. As I said, we are continuing to work on that problem, and our initial calculation just for simplicity, just to fix the number of conduction electron when you go. Indeed, I think the number of conducting electron on the 5D, lantern or revealing will be reduced. Yeah. So we are going to do that calculation. The difficulty is we do not know how you increase the hold on the nickel side, and at the same time reduce the number of electrons. So need some parameter. Yeah, we are waiting for some first principle calculation. If anyone has the kind of suggestion, I think that would be great. By the way, because you raised the point when you dope, okay. I think that there's also a proposal I'd like to mention that because the field is just quite new, still developing. Okay. And all theory would have to face the experimental test or to some extent to be tested by the first principle calculations. It's in some kind of interest. So there are proposals for the whole length. Actually, they want to say it's spin 1. Okay. The reason is if you have the whole length, it's D8. D8 means two electron missing. So in all calculation, we assume it's just all D extra minus Y square electrons are empty. Okay, and the other D electrons are occupied. But there's also a proposal of argue that probably due to Hund's rule, you have one electron on the D square and one electron on the D X square minus Y square orbital. So that forms a spin 1. And that's also an interesting possibility and for the doped case. But I'd like to, we have did some simple calculation for that case. If small perturbation, it does not matter. If it was a large case, just all these the holons becomes a spin 1, then the physics may be different.
Okay, thank you.
Okay, any other question from audience? Let's see. Okay, I think everything is very clear. The model is very simple and the mean field calculation is rather straightforward. So we have to wait more experimental data to confirm your proposal, I think.
Yeah.
Okay, with this, we will end today's seminar. And don't forget, Professor Fu-Chun Zhang will give his second seminar tomorrow about different subject. Majorana zero mode in topological superconductor. I guess he will give us some general overview as well as some new insight how to look at this Majorana zero mode in the topological superconductor. So thank you very much, everybody, and let's see you tomorrow, same time. Enjoy your
Okay. Yeah. Okay. Thank you. Bye.